we have two like great talks in this session, then a break, which here is like a tea time. If you don't know what that is, prepared to like be amazed. Before we start our own talks, we're gonna have a panel this afternoon after tea time. And like don't forget, if you have any questions you want our panelists to address, email them here. I don't want to like spell it out because it's hard to spell. It's a lot of letters. I'm sorry. Bye, Dave. Where are you? Anyways, email them there, and they will be a part of our conversation. But now I'm absolutely thrilled to introduce Wanrong Zhang, who is a Harvard postdoc, supervised by Salil, working on some awesome privacy stuff that she apparently submitted today, 20 minutes ago. So it's very fresh. Yes, exactly. And I will shamelessly plug, she's also I'm going to be on the job market this year. And so if you like this talk, then you should hire her. But of course, Wanrong. No pressure. So that's so before we hand over the stage, if you have any questions during the talk, raise your hand and I'll bring you the mic so that Zoom folks can come here. And for Zoom folks, type them in the chat if you have any questions during the talk. And then again, at the end for the Q&A. So welcome, Wanrong.
So for the introduction, I'm Wanrong Zhang. I'm currently a postdoc at Harvard. And today I'm going to talk about my very recent paper on concurrent composition theorems for differential privacy. And this is joint work with my postdoc advisor, Zhang. So to get started, I want to do a quick recap on the basic concepts, the differential privacy and the composition. So differential privacy ensures that one person's data won't change the distribution of an algorithm's output too much. And in this way, it can make sure that the information leakage for one person's data is going to be bounded by a small amount of information leakage. And this small information leakage is quantified by the privacy parameter epsilon. And for the composition, and this is a very basic property about differential privacy, which is very nice. It says, suppose we have k mechanisms, and each mechanism is epsilon differentially private. And then suppose we are running them sequentially, and then the overall privacy loss for the whole system is going to be k times epsilon, and which means the epsilon just add up. And this is a very nice property about differential privacy because it allows us to design a complex DP mechanism by combining several building blocks. And here we are making a very important assumption, is we have to run each mechanism sequentially. But in practice, and suppose each mechanism involves several rounds of interactions, and we may want to run the key mechanisms concurrently at the same time. As an example, when I use my mobile phone and for example, when I use search engine or read an email in Gmail, I may interacting with Google, which is possibly an adversary. And suppose I use a epsilon DP mechanism to answer Google's query. And then at the same time, I may also want to look at some social media platforms, like I'm going to scroll Instagram or Facebook. And then I'm gonna interacting with Facebook, which is also possibly an adversary. And suppose I also use an epsilon DP mechanism to answer Facebook's query. And the question is, what would be the overall privacy loss in this system? And you may think, oh, it's just going to be 2 epsilon, because we can use composition theorems to reason about that. But to use this, to have this conclusion, we actually make an assumption that the Google and Facebook, they cannot talk to each other. And in this way, the query issued in Google and Facebook, they're independent of each other. So then the privacy laws are independent of each other. then we can use the sequential composition theorems. But the question is, what if they can talk to each other? And for example, if the query from Facebook can depend on the query then received from Google in previous rounds. And the same, and similarly, the query from Google can depend on the answer then received by Facebook. And in this way, it's not clear if they can run some concurrent attack to break the privacy guarantee, because the privacy, because of the adversary strategy may change. And we are no longer talking about the fixed adversary strategy. So we're currently lacking a tool to reason the total privacy loss in this concurrent composition setting. And this is a local model. And the concurrent composition, the concurrent interactive analysis is also common in the central model. And for example, as a Harvard employee, I can choose between the two healthcare systems each year. And suppose this year I'm using the Blue Cross Blue Shield. And next year, I may want to switch to the Harvard own system. And suppose, so they both have metadata. And this is medical data and it's highly sensitive. And suppose an adversary can concurrently query the two systems. And the two organizations, they both use an epsilon DP mechanisms to answer the adversary's query. But they don't know then the adversary is querying another system concurrently. Then the adversary here can arbitrarily interleave its query to the two systems. Like the query sent to the Harvard system can depend on query received from Blue Cross Blue Shield. So then the adversary can inject some correlations between the two systems. And it's not clear if the overall privacy loss is still 2 epsilon in this case. So again, the existing analysis assume that the adversary have to finish and query the first one and then move on to the next one. But in many practical settings, they are doing that concurrently. So it motivates us to study the problem of how to account the total privacy loss in the concurrent composition setting. Question?
Just a really basic question about like a CP. Like,
sure.
Am I allowed to just keep querying the same point? Like, if there's only one company.
And can you repeat the question, please? Oh yeah, sorry, I have a mic that I'm supposed to pass around.
So your question is, can I ask the same question again and again?
Like it's something, yeah, exactly, in just the basic model. Like, can I just query the same point? And
Yeah, we can query the same point.
And I won't get new randomized responses, or I won't get new noise. I'll just be given the same.
You will have new noise every time.
Okay.
Yeah.
All right, thank you.
But the privacy loss will going to grow up.
Oh, okay.
Yeah.
And yeah, so it'll like concentrate.
Yeah, concentrate. Yeah. Each time you will have fresh noise. So to give the background, I'll first introduce the definition of interactive differential privacy and interactive mechanisms. So I assume this audience have seen this classical definition of differential privacy before. And this is, we see an algorithm then is epsilon delta differentially private if for all pairs of neighboring databases and for all possible outcomes. The probability over the outcome on 2 neighboring databases must be close in this epsilon delta closeness notion. And when delta is equal to 0, and we'll just say it is epsilon dp, which is also pure dp. And this epsilon delta differentially private requires approximate dp. So So based on other notion of measuring the closeness, we have also seen several variants of DP in literature. For example, we have concentrated DP and Rayleigh DP, which are based on the Rayleigh divergence. And we also have the FDP, which is based on the trade-off function between the type 1 and the type 2 error that's distinguishing the 2 neighboring databases. So all these definitions only considers non-interactive mechanisms, then release query answers in one shot. So, but often we want to do interactive analysis. Like we want to first do some summary statistics and then do some fine-grained analysis. Or like we want to have feature selection and then do regression. So the interactive mechanism allows the analyst to ask an adaptive sequence of queries about a data set. And to formally define interactive mechanisms, we are using the classical definition of interactive protocol in the crypto literature. So here we view the interactive mechanism as a party in an interactive protocol. And it has, so each party has three components. So the first one is a private input. And here, the private input of the DP mechanism is just a data set. And the adversary, there's no input, so we'll just leave it as a blank. And they all have random coins. And the random coins capture the randomness of producing a query or the answer, which sent to each party. And they also have a function that takes all previous histories and produce an answer, then sent to the other party. So, and in fact, there are many useful primitives in differential privacy has already been interactive. For example, the sparse vector technique and also the private multiplicative weights. So to define interactive differential privacy, we also have another definition, which is the view of a party in an interactive protocol. So this is, again, the classical definition of view in the crypto technique, crypto literature. So in the DP setting, we only care about the view of the adversary. So first, it has the random coin components, and it doesn't have any input. And only the mechanism has an input. So we will denote A interacting with M take X. And there's no private input for the adversary. And those are the messages then A received from the mechanism. So here's the definition, the view of the adversary interacting with this interacting mechanism. So with this definition, now we can define the interactive differential privacy. So interactive differential privacy is defined by asking for the views of an adversary on two neighboring databases, satisfying the same epsilon delta closeness notion as we just said before. Here's the formal definition. So basically, instead of having the distribution of one-shot release, we're going to model the probability of the views of the adversary. And also, I want to highlight this additional constraint here. Now we are considering all possible adversary strategies. And before, we only talk about a fixed adversary strategy. And so we have to satisfy this epsilon delta closeness notion for all possible adversary strategies for interactive mechanisms. So now we talk about composition. So as I mentioned earlier in the talk, composition is a very basic fundamental property of differential privacy because it allows us to build a complex DP algorithm by several building blocks. And we have the basic composition theorems. It says if each mechanism is epsilon I differentially private, then the overall privacy loss is just going to be we add up all the epsilons. So basically all the epsilon adds up. And for advanced composition theorems, we improve on this bound and show that the privacy parameter grows linearly. And here is a sublinearly, and this is linear. And then here actually is a square root of k factor. And we also have optimal composition theorems, which gives the exact characterization of the privacy guarantee under the k-fold composition. But they show that to calculate this bound is actually NP hard. And we also have other variants of differential properties, ZCDP and RDP and FDP. And they allow for tighter reasoning about composition. And all these works are considering non-interactive mechanisms. But some of the work, they are framed in a way that the mechanism can adaptively choose, the adversary can adaptively choose the mechanism. So the adaptive composition can be viewed as one interactive mechanism. So like we're composing a sequence of non-interactive mechanism, and the overall can be viewed as a one interactive mechanism. And the question for us is how to do composition for multiple interactive mechanisms. So it can have two categories. The first one is sequential composition of interactive mechanisms. And it's so obvious that the proof of composition theorems of non-interactive mechanisms can be directly extended to sequential composition of interactive mechanisms, because we can reorder everything. So everything can be viewed as a sequence of non-interactive mechanisms. So it can be easily addressed. And the interesting case is a concurrent composition, where we want to perform multiple interactive analysis on the same data concurrently. And the concurrent composition was first studied in Zhang 2021 for differential privacy. And before that, it was actually studied extensively in the crypto literature. And it's often more subtle compared to the sequential composition. And for example, the standard zero knowledge proof is no longer the protocol. Standard zero knowledge protocol is no longer zero knowledge under the concurrent composition setting. So our goal is to say if the concurrent composition will make things worse for differential privacy setting. So in the concurrent composition for differential privacy, we look at this picture. So again, the queries can be arbitrarily interleaved in the K mechanisms, and the query sent to M2 can depend on the answer received from all other mechanisms. And the question is, what is the total privacy loss in the K concurrent systems? And you may wonder, because there's many rounds of interactions, and what if we can reorder everything and use sequential composition to address this problem? So let me explain this. Like for example, first of all, in many cases we cannot reorder all the queries. Like if one is feature selection and the other one is regression, we cannot reorder the queries. But suppose we can reorder the things. Like if the two mechanisms are all sparse vectors, and we can reorder the queries. And suppose like the adversary add the first round of queries to M1 and get the answer, and then go to M2 and to ask a query and get the answer, and then go back to M1 to do another round of induction, and then go back to M2. And suppose the adversary do this in go back and forth for K times. Question.
I know this is a very silly question, but the reason you can do that is because they're happening at the same time.
Yeah.
So you can just do whatever order you want. So,
Yeah, presume.
sorry. So yeah, so you can do that reordering because it's concurrent.
Yes.
Yeah. Okay.
I can do the reordering for some specific cases when the query has some order. But for like feature selection and regression, you cannot reorder the things. So what I'm explaining here is, even if we can reorder them, we'll say we have some worse guarantee if we just directly use sequential composition. Yeah. So like if we go back and forth for K times, and suppose each sparse vector is just epsilon dp, and then we do this for K times, then we will have 2 times K times epsilon over our privacy loss. And we have this additional factor of K, which we don't want it here, because actually we only have 2 sparse vectors. Ideally, we only want to have 2 epsilon privacy loss. So directly using sequential composition is not sufficient. That's why we have to have a guarantee for the concurrent composition. Any questions on this example? Okay, good. And the only existing result on concurrent composition is the previous paper showed that the advanced and optimal composition theorems extend to the concurrent composition of interactive pure DP mechanisms. But for approximate DP, which is epsilon delta DP, they show that the overall privacy loss is this. And this actually is a proof privacy-like bound. And this is even suboptimal compared to the basic composition when the privacy parameter just grow linearly. And this is bad. So it left an open question as if any composition theorems for non-interactive mechanisms can extend to all other variants of differential privacy, including approximate DP, RDP, and FDP. And in our paper, the answer is yes. The composition theorems for non-interactive mechanisms can be extended to the interactive concurrent setting. And we don't have additional privacy loss. And which formally says as this. Suppose that we, for all interactive mechanisms, and 1 to mk, such that each mi is epsilon I delta I dp. Their composition is epsilon delta dp. Then for all interactive mechanisms, M1 to mk with finite communication, such that each mi is epsilon I delta I dp. The concurrent composition is also epsilon delta dp. So basically, it says that in all composition theorems for non-interactive mechanisms for approximate DP can be extended to the concurrent composition of interactive approximate DP mechanisms. And we don't incur additional privacy loss in the concurrent composition setting, which is a very nice thing because in practice, in the practical deployment of differential privacy, we don't have to ensure that every mechanism is running sequentially. And we can allow the full interaction in the DP systems. And we can allow the multiple full interaction in several systems, which is a very, very nice thing. And we also show that the similar results hold for the FDP, which is a more general relaxation of differential privacy that's based on the hypothesis testing interpretation. And because the theorem 1 follows directly from theorem 2, for the rest of the talk, I'll only focus on the results for FDP.
Can I ask a quick question?
Sure.
This point about finite communication, is that critical in some technical way?
Yeah, because we are using induction in the proofs. So we have to make sure the interaction has finite number of rounds. So that's why, yeah. So some of you may not be familiar with FDP. So this is a generalization of differential privacy based on the hypothesis testing interpretation. And we are considering a simple task. So the H known is the data set is X versus the data set is X prime. And then we let the random variable Y and Y prime on the be the output distribution of M on X and M on X prime, and let the phi be the given decision rule. And then we can write the type 1 error, which is the probability of rejecting H null when H null is actually true. And we can also write type 2 error as this. The type 2 error is the probability of failing to reject H null when H1 is actually true. Then with type 1 error and type 2 error, we can define the trade-off function between the two types of errors. So basically, the trade-off function quantifies the achievable and unachievable boundary of the two errors, of this simple hypothesis task. And then for FDP, we are defining FDP as within an algorithm is F differentially private if for all pairs of neighboring databases, we have the trade-off between the two output distributions is going to be greater than F. So the FDP basically allows a full trade-off between the type 1 error and type 2 error of this simple hypothesis testing task to be governed by this F. So it's a larger F implies a stronger privacy guarantee. And so this picture.
Is this for a particular rule or for the best rule?
For the best rule. So here we are taking the informal over all possible decision rule. So this is the optimal boundary between achievable and unachievable errors. And like this picture illustrates the trade-off between the two errors. Like suppose this solid curve is a target F, the target trade-off function. And then only this curve that's above the target F satisfy FDP guarantee. And for all other two curves, they're below the target F for a certain region. So they are not FDP. A few examples. For approximate DP, actually this piecewise linear trade-off function is the trade-off function for approximate DP. That's why approximate DP is a special case of FDP, and we're gonna just focus on the general FDP proof. And many of you may be more familiar with GDP, the Gaussian DP, because we usually use this to account for the privacy loss for DPSGD. So this is a parametric family of FDP, which we consider the trade-off function between two Gaussian families. So here's our formal results on the FDP, which basically says all composition theorems of non-interactive FDP mechanisms can be extended to the concurrent composition of interactive FDP mechanisms. So for FDP, we don't incur any additional loss in the concurrent composition setting. So how to prove this? And our proof actually relies on this nice reduction theorem from interactive mechanisms to non-interactive mechanisms. So this theorem basically says for all given trade-off function F and for any interactive FDP mechanism M with finite communication, and for all pairs of neighboring data sets X and X prime, there exists an non-interactive FDP mechanism N and a randomized interactive post-processing T, such that for all possible adversary strategy, we have the view of the adversary interacting with M is identically distributed to the view of M of the adversary interacting with T, then takes the N of X as the input. So how to understand this theorem? So basically, we can look at this picture. So basically, this theorem says for any interactive mechanism M, it can be decomposed into a non-interactive mechanism N, which takes the data set as the input, and then produce an answer sent to a post-processing function, T. And this post-processing function does not take the data set as the input. It only takes the output of the N of X as the input, and then interacting with the adversary just as M does. So that's why we call it a interactive post-processing function, but it does not take any database as an input. So basically, the T simulates all the answers just based on the N of X. So basically, this theorem says any interactive mechanism can be simulated by non-interactive mechanisms. So we can reduce an interactive mechanism to a non-interactive mechanism. So this is reduction theorem. And a few special cases to understand the non-interactive mechanism. So we show that every epsilon delta dp interactive mechanism can be simulated by the epsilon delta randomized response. And Christina introduced the randomized response earlier in the morning, and which is good. And in fact, the previous paper showed that the similar results for every non-interactive dp mechanism can be simulated by the epsilon delta randomized response. But we extend them to the interactive mechanism. And the challenge here is we have to show the T has to be universal, then satisfy all possible adversary strategies, and which is a major challenge for the interactive mechanism. And in the previous concurrent composition paper, they also show that every epsilon interactive mechanism can be simulated by the pure dp randomized response. And this reduction theorem has a nice implication on the concurrent composition. So basically, to analyze the concurrent composition of k interactive mechanisms, it's equivalent to consider the concurrent composition of the post-processing that takes the non-interactive mechanisms. So the sequence of this. And because this T does not have any data set as input, which means we need only consider the composition of these non-interactive mechanisms. And as a result, the composition theorems for non-interactive mechanisms extend to the concurrent composition of interactive FDP mechanisms. And so we don't have any additional privacy loss in the concurrent setting. And we show that by this reduction theorem. Okay, this is the story for the FDP. And this reduction theorem also has a nice implication, even without the application to differential privacy. So like when we talk about the hypothesis testing, and we are so normally we talk about the non-interactive hypothesis testing, where we generate a sample, then and send to the hypothesis tester, and the hypothesis tester is going to distinguish between whether this sample is generated from H0 or generated from H1. And suppose now we consider an interactive hypothesis testing task, where the task is to distinguish between two interactive mechanisms, M0 and M1. And suppose each mechanism responds to queries in randomized and stateful manner. So what is this stateful manner? It says the hypothesis tester cannot find how the mechanism would have answered if different queries had been asked. So it says the hypothesis tester may never know everything about the whole distribution, about the full distribution. So it sounds like a much harder setting, much harder task to distinguish. But if we view the M0 as a M taking X and M1 as M taking X prime, then by our reduction theorem, we can actually show that they can be simulated perfectly by a non-interactive mechanism. The N0, which is N of X, and N1 is N of X prime. So this means even if we give N0 and N1 to a hypothesis tester in its entirety, it cannot distinguish them any better than it would distinguish M0 and M1. So this is a very surprising finding that for the interactive hypothesis testing task, we are actually won't do worse than the non-interactive hypothesis testing task. All right, so this is story for FDP. Now we are going to talk briefly about the RDP. So there's a independent and concurrent work by Liu, 2022, and they proved that the similar results hold for approximate DP And this theorem is same as ours. And they also show the similar results hold for RDP for a fixed alpha. And this is the parameter for the RNA-DP. So as a comparison, we have the same results for approximate DP, but we have different extensions. In our paper, we show the FDP, and in their paper, they show the RDP for fixed alpha. And we actually also give a simple proof for RDP, but technically their results is their proof is earlier than ours. So I'll just briefly mention our simpler proof here. So we prove this by characterizing the optimal alpha RDP adversary strategy against an interactive mechanism. And then so this is the optimal strategy against one interactive mechanism. And then we also characterize the optimal adversary against the concurrent composition of the K mechanisms, which shows that it can be decomposed as the optimal adversary against each mechanism independently. And the overall optimal adversary can be viewed as a product of this the set of optimal adversaries. So in this way, we can view each mechanism independently. And then we can sum up all the privacy loss, which is identical to the optimal composition for the non-interactive mechanisms. So in this way, we show that we also don't incur any additional loss in the concurrent composition setting for RDP. So I'd like to stop here. As a conclusion, we prove that all composition theorems for non-interactive differentially private mechanisms extend to the concurrent composition of interactive differentially private mechanisms for approximate DP and FDP. And we show that by the reduction theorem that every interactive FDP mechanism can be simulated in by the interactive post-processing of an interactive FDP mechanism. And we also give a simpler proof of Liu's concurrent composition theorem of RDP. So combining all this together, we can claim that we don't incur any additional loss for the concurrent composition of differential privacy, which is a very nice property for the practical deployment of differential privacy, which means we can allow the full interaction in multiple systems, and we don't have to force them to be sequentially composed. And thank you. I'm happy to take any questions and comments.
Fantastic. Thank you, Wanrong. So we have plenty of time for some questions. Who wants to start? All right.
Hi. Thanks for your talk. I was just wondering for like the post-processing mechanism T, does it depend on which interactive protocol you're using? Interactive mechanism you're using, or how do you find that?
So this T definitely depends on M. So your question is how to find the interactive post-processing function. Whether this T depends on M. Yeah. So this interactive post-processing function in practice you can find this by you can derive a set of functions and derive which output of N then take to produce an A. So the T have to satisfy a set of functions, and you can have this T by simulations. And our theorem just show the existence of the T, but in practice it really depends on the specific mechanism M, and you have to solve that by the computer experiments.
Other questions? We have one. So you mentioned at the beginning, at the very beginning, things like sparse vector as being like examples of this kind of like adaptive composition. before you began all of your results.
Mhm.
What are some new types of mechanisms that we couldn't analyze before, but we can now, where we can like analyze them in a better and tighter way with these results?
So, so the sparse factor is one example, and before the composition guarantee is to analyze several sparse vector running sequentially, because like we can like finish one sparse vector and then run the other sparse vector. But now if we have k sparse vector like running at the same time, running at the same time, and now we can analyze the overall privacy guarantees if they are running like concurrently. So even sparse vector is a simple example. The previous analysis still does not allow us to reasoning about the total privacy loss for the k sparse vectors, because as I showed here, we'll have much worse privacy loss.
Other questions? All right, then we can thank Wanrong again.